So these are the notes for rational exponents. So the first thing we have is the definition for the nth roots. It says x is the nth root of a real number a if x to the n equals a. So from here it says the nth root of a real number a can be written as the radical expression the nth root of a. Now the way they came up with that expression was they took x to the n equals a. To get rid of that power of n, you take the nth root on both sides. And when you take the nth root, you see that x is equal to the nth root of a, which is this expression right here in the middle. Now, when we look at this radical here, the n is called the index. It's the root of the radical. Then that sign that most people call square root is actually called the radical sign. And then the a is inside the radical, which we call the radicand. If there is no index, it is assumed that n is equal to 2. So what does that mean is, like, whenever we have a radical sign and there's no power, automatically everybody calls it a square root. So by default, they assume that in the hook is a 2. Whether they know it or not, that's what they're assuming. All right, for the rational exponents, it says expressions with rational exponents can be rewritten as radicals using the following rules. So we have our exponential form right here. And rational exponent just means rational is a fraction and exponent is your power. So right here, if you look at this 1 to the n power, your exponent is a fraction. And same with the one below as well. So these are called our exponential forms because they have a base raised to a power. Now we're going to look at the conversion to the radical form. So one thing I want to point out first is that whenever you have that rational exponent, on the top of the fraction is the power, and on the bottom is the index. Okay, and you'll hear me say index and root interchangeably. So over here, so if you look, the power is 1 and the index is n. So over here in the hook, that n is the index, and then there's no power of 1 here, so you can put it, but it's assumed to be there. Now for the second one, we have a raised to the m over n. So again, m is in the power position and n is in the index position. So when I rewrite it, notice the index goes in the hook, the n goes in the hook for the index. The a, the base, is the radicand that goes inside the radical, and then m, the power, goes on the outside. Now there's a second way you can rewrite this if you choose to, but you can write it as the nth root. Let me move this over. The nth root of a, you can put the m inside the radical if you choose to. Okay. All right, so these next ones say converting exponential to radical form. So write each expression in its radical form. Okay, so I'm going to start with a radical sign first. So remember, the index, the bottom number, that is your index. So the 4 goes in the hook. My radicand is the base, which is x, in parentheses, raised to the power, which is 3. All right, for the next one, k raised to the 7/2. So again, we start with a radical sign. Now the index right here is a 2, but we know that it's assumed to be 2 if we don't place anything there. So I'm not going to put the 2 in there, but if you'd like, you can. It would not change it. K, and then the power is 7. So the square root of k to the 7th power. And last, for number 3, we can see that 15 is not inside the parentheses. So that 15 is actually outside of the radical. So inside the radical is x. Again, we have another index of 2. So if you want to put the 2, you can, but it's understood to be a square root. And then my power here is 3. So 15 square root of x cubed. All right, for evaluating radicals, if you look at these 3 problems here, they are all cubes. So we're going to talk about cube roots. And hopefully you understand that the cube root of 8 is actually 2. And you can always just break that down, like 4 times 2 and 2 times 2, and since it's a cube root, we're looking for groups of 3, so we have 1, 2, 3 2s, which gives us a 2. The cube root of 343 is going to be 7. And now this one is interesting because we have a negative in there, but since our index is odd, we can have a negative real solution. So hopefully you recall that the cube root of 125 is actually 5, and we have that negative inside, so that makes it negative 5. All right, next it says converting radicals to exponential form. So write each expression in its exponential form. So again, we're looking at that form. So this one is the nth root of a raised to the m power, which gives us a raised to the power over the index. Okay, so for this first one here, I like to identify what the power is. I can see the index is 3, but the power is a 1 there. So I start with my base, which is the radicand, 16. raised to the power over the index. So 16 raised to the 1/3. For this next one, again, the power is 1, but we notice this 5 is on the outside of the radical, so 5 parentheses xy. Now, since there's no power inside the hook for the index, it's assumed to be a 2, so it's going to be power 1 over index 2. For number 12, same thing. I have a radicand of 8w squared, so that is my base. The power is a 1 on the outside, and my index we can see is 4, so it's going to be 1/4. All right, now one thing I want to point out about number 13 is kind of what I talked about right here. These are equivalent. Let me fix it real quick. These right here are going to be equivalent. So let me show you over here what that means. So I told you that the nth root of a in parentheses raised to the m power is equivalent to the nth root of a raised to the m power inside. Okay. First thing I want you to notice is there's only one term here and one term there. Now, for the most part, I stick with this first one, but here I'm going to use the second one so we can relate it to that. So I can actually take that cube root of 11 squared and rewrite it as the cube root of 11 squared on the outside. So when I go to convert it to its exponential form, the radicand is my base of 11, and its power, the power is 2 over the index of 3. For number 14, I can do the same thing. I'm going to rewrite that as the 4th root of k to the 10th power. So then I have my base power over index, and that can actually be reduced. So 10 over 4 becomes 5/2. And then for the last one, it's pretty straightforward. We have the square root of 3m raised to the 7th power. So our radicand, our base is going to be 3m. Our power is 7, and our index, remember there's no number there, it's a 2, so 7/2. Okay, last we're coming down to this part here where it says radicals with variables. So again, recall that it's a power over index for the rational exponent. But over here I have a little table where I have the perfect squares, the perfect cubes, and the perfect fourths. And you'll notice for perfect squares, you can go as far as you want. Most people can just do that in their head, or they can use some utensil to get there quicker. For the cubes, 2 cubed is 8, 3 cubed is 27, and so on. But I usually won't go past really 343. I wrote 512 there for the 8th one, but I really don't go that far. And for the 4th one, I usually stop at 625. Now, I put the 1 there, but honestly, it's not necessary because anything 1 raised to any power is always going to be 1, so that's really not necessary to have. Okay, so let me kind of show you how this works. So over here, it says if we deal with square roots, then the exponents must be a multiple of 2. If we're dealing with cube roots, we want the exponent to be a multiple of 3. And if we're dealing with 4th roots, we want the exponent to be a multiple of 4. Okay, so from here, let's go ahead and look at this here. So for my first one, I have the square root of x to the 4th, y to the 9th. So since it's a square root, I'm looking for multiples of 2. So first I'm going to start with this x to the 4th. Let's change the color here. So I have x to the 4th, and we know that 4 is a multiple of 2, so we're going to leave that alone. But when I get to y to the 9th, what is the largest multiple of 2 that goes into 9? Well, that's going to be the 8th power. Okay, so we have the 8th power. But that extra 1 over, we have to write it. And really quickly, if you're not sure about this, properties of exponents say when I split it apart, this is an 8 and this is a 1, so 8 plus 1 is 9. So it's actually the original 1. Now I'm going to take my square root and put it above this. Now, again, recall my index is 2. So what I'm going to do is I'm going to take each of these exponents and divide it by 2. If it becomes a whole number, I'm going to pull it out of the radical. If it's not a whole number when I simplify it, then I leave it in the radical. So for this first one, 4, we're going to divide by the index of 2. So 4 divided by 2 is 2. So we pull it out and it becomes x squared. For the next one, we're going to divide 8 by 2. And 8 divided by 2 is 4. That's a whole number, so we're going to pull that out. So y to the 4th. Now this last one here, when you divide by 2, it doesn't work. So I'm going to circle that. And that goes back in the radical. So it's going to be the square root of just y. We don't have to put that 1/2 because the 1/2 is the square root. All right, for number 10, we're going to follow the same process. This time, it's going to be a 4th root. So we're looking for multiples of 4. So whatever that index is, we're looking for multiples of that number. So for this one here, we'll start with w to the 4th. And 4 is already a multiple of 4, so we can leave that alone. For the v to the 17th, we're going to break that into the largest multiple of 4 that goes into 17 is 16, leaving me with v to the 1st left over. Now we're going to put our radical over there. And again, we're going to divide by our index. Our index is 4, so 4 divided by 4 is 1, so that's going to be w to the 1st on the outside. For v to the 16th, we're going to divide that by 4, so 16 divided by 4 is 4. That's a whole number, so we move that to the outside. And last, this v to the 1, we know it's going to be 1/4, so we're going to circle that because that reminds us that it goes back inside of the radical sign. So wv to the 4th times the 4th root of v. All right, for number 11, now we have numbers, and now we'll start using that little table here. So the first thing I'm going to want to do is I want to take that number and I want to break it down. So we're looking for the 4th root. So I'm going to go to the column that's dealing with 4th roots, which is right here. And I'm going to take these 48 and I'm going to divide it by each one. I'm not going to use 1, but I'm going to start with 16. 48 divided by 16 is 3, okay? And I just got lucky off the first one it works. So 16 times 3 is 48. Now, how do I know when to stop when the largest perfect whatever it is goes in there and I can't go any further? Like 16 is the biggest one that goes into 48, and I can't go any further than that because 81 is already bigger than 48. Okay, so right here, next thing I'm going to do, I'm going to start breaking these down. Well, if you notice, you look at the previous examples, all of them I had raised to an exponent. 4, 8, 4, 16. So this 16 right here, I need to break that into a perfect 4th power, right? So over here, if I go it, so I'm looking at right here, it is 2, and I was raising it to the 4th power. So that's where it comes. So it's like kind of like a little chart. So 2 to the 4th power makes 16 times the 3, and the 3 is right here, so I'm not changing anything. Now, if I look at my m has a power of 8, which is already a multiple of 4, so I'm not going to do anything to that. My n, however, is not. But the problem with the n to the 3rd, it's impossible for me to make that to a 4, so I'm just going to leave that alone. I'm now going to take my radical 4th root over it. And again, this will be the last time I divide, so hopefully after this time you realize that I'm dividing by the index. So I'm going to divide this by 4. So 4 divided by 4 is 1, so that 2 comes on the outside. Here we have just a power of 1, so I can't divide that by 4 because it'll be not a whole number. We'll divide this by 4, so 8 divided by 4 is 2, so that's m squared. And then 3 divided by 4 is not a whole number, so I'm going to circle that. And back inside the radical is going to be 3n to the 3rd power. All right, on to number 12. For number 12, you'll notice there is a 2 on the outside, so we're going to leave that there. The 56, we're looking for perfect cubes. So right here, I'm looking in this column, the perfect cube column. So the first one I divide by is 8. So 56 divided by 8 is 7, and that's actually the biggest perfect cube that fits in there. So now I'm going to start my whole process of breaking this down. So I start with the 2 on the outside, because that's right there. Now you'll see when I put the cube root, I'm going to exaggerate it just because I don't know how much stuff's going to fit in here. 8 right here, I can take that. That's going to be 2 cubed. So 2 cubed is 8 times 7. Now this time my index is 3, so I'm looking for multiples of 3. So the largest multiple that fits into 8 is, largest multiple of 3 that fits into 8 is 6. So that's going to be r to the 6th, and that means r squared would be left over. My largest multiple of 3 that goes into 4 is going to be 3. So that means s to the 1st will be left over. All right, so now I'm going to divide by 3. So first I have this 2 on the outside. I'm going to divide this by my index of 3. So 3 divided by 3 is 1. So that 2 comes on the outside is 2 to the 1st power. This has a power of 1. It can't be divided by 3. This 6, when I divide it by 3, 6 divided by 3 is 2. So that becomes r squared. And I'm going to cross these out so I don't reuse them by accident. R squared, so 2 divided by 3 is not a whole number. So I'm going to circle that because it'll go back in the radical. For the s, 3 divided by 3 is 1. So that comes on the outside. And this last one has a power of 1, and when I divide it by 3 is 1/3, so I can't do anything, I leave it alone. And last but not least, before I write what's left over in the radical, I'm going to simplify this outside. So 2 times r squared times s is going to give me 4r squared s. And now I'm going to start with my cube root. and I have a 7, r squared, and an s. And this will be my simplified radical. All right, looking at the next one, number 13, we have the cube root of negative 64, 10 x to the 10th and y to the 21st power. So this one, we're looking for those perfect cubes. Now over here, I noticed for the cube, 64 is already a perfect cube. So if you look right here, it's 4 to the 3rd power, and it's negative. So I'm going to make it negative 4 to the 3rd power. Okay, and I do need that negative 4 because a negative 4 times a negative 4 is a positive 16, but times that negative 4 for the third one is going to be negative 64. So I do need that negative there. Now, I'm looking for multiples of 3. So the largest multiple of 3 that fits into x to the 10th would be x to the 9th, leaving me with 1x over, times, now 21 is already a multiple of 3. So again, we're going to divide by our 3 now. So 3 divided by 3 is 1, so I have a negative 4 coming out. 9 divided by 3 is 3, so that's x cubed. This one cannot be simplified because that's a 1/3, and then 21 divided by 3 is 7. So left over, the only thing left over was that x, so that's the cube root of x. All right, and now we're down to number 14. Again, number 14, if you look, negative 81, we're looking for the cube root. I don't see that there. So if I did take 81 and divide it by 8, that actually gives me a fraction or a decimal, so that doesn't work. If I take 81 and divide it by 27, I actually get 27 and 3. Whenever you have that negative in front and you're simplifying it, you always want to put it with the perfect square, cube, or 4th power, because when you take the root, you're going to pull that out. Okay, so negative 27, so if I go back over here, so 27 is going to be 3 cubed. So we're going to write that as negative 3 cubed times that 3 there. So that's negative 3 cubed. For the p squared, I can't break that apart to be a multiple of 3, so I'm going to leave that alone. And then q to the 12th, 12 is already a multiple of 3, so I don't have to actually do anything to that. And now I'm going to divide by my index. So 3 divided by 3 is 1, so we have a negative 3 on the outside. This one has a power of 1, so when I divided by 3, it's a fraction. This one as well, p squared, so 2 divided by 3 is 2/3, that's not a whole number. But the q, 12 divided by 3 is 4, so that's q to the 4th. So back inside the radical, what we circled was 3p squared. So this is my simplified radical. All right, we're down to the last 2 here. So for number 15, we have a square root. And the good thing for us that 324 is actually a product of 18 times 18. So we're going to start with this 3 here. We're going to do a square root. So this 324 is actually 18 squared. So I'm looking for squares, right? Perfect multiples of 2. So a to the 3rd can be broken into a squared times a to the 1st. And the b can be broken into b to the 6th times b to the 1st, where you'll see the a squared, the 2 is a multiple of 2, and 6 is a multiple of 2. Now we're going to divide by our index of 2, so start with the 3. 2 divided by 2 is 1, so we have 18. 2 divided by 2 is 1, so we have an a on the outside. This one is going to go back inside because 1 divided by 2 is 1/2. 6 divided by 2 is 3. And this one, again, you divide it by 1/2, you get a fraction, so we're going to circle that. It's going back in. So before I rewrite my final answer, 3 times 18 is 54. Then we have ab to the 3rd. Then we have the square root of ab. And there's my answer. All right, number 16, we're looking for perfect cubes here. This one will be pretty quick because if you go to the 216 in the cubes column, you'll see it's actually already there, right? It's 6. So the cube root of 216 is actually 6. So we can say 6 cubed times m cubed. 3 is already a multiple of 3. And just like n to the 6, 6 is a multiple of 3 as well. So when we divide these by 3, so 3 divided by 3 is 1, so that's a 6. 3 divided by 3 is 1, so that's an m. And 6 divided by 3 is 2, which is n squared. And that's going to complete the notes for today.